Alright, so today in the next part of the sampling distributions, we start to look at a couple of the distributions. So first of all, distributions of sample proportion. So that's the proportion in the sample that have a particular characteristic. And so there's two types of random variable that we need to look at. So first one up there is it says discrete random variables. So you have whole number values. So often they're counted. So those sorts of things for discrete. So if you think, do I count that? And you go, oh yeah, I do. Then it's random. The other type of random, it's discrete. It is random, of course, but discrete as well. The other type of random variable is one that you can have any value whatsoever. And so these are often measured, and if you've got a good enough measuring instrument, you could go to many decimal places. So the key things that I like to think about in knowing whether it's discrete or continuous is count, measured. If you count, it's discrete. If you measure, it's continuous. And there's very few exceptions there. The only things that I would think of is, like, say, shoe size, for example, is a discrete because it goes up in particular amounts. All right, so 2, 2.5, 3, and so on. All right. Okay, so that's a little bit of a waffle there. So probability distributions. So let's look at how the probability of things might be distributed. And so discrete ones we're going to look at first. So this one here, we're going to consider a coin, and we're going to throw this coin 3 times. So here, I've already prepared earlier what all the possible outcomes are. Let me change my pen colour. Let's go orange, shall we? All right, so the first one here, all these first ones say this is what you might get the first time. All right, and then the second column's what you might get the second time, and then the third time. So one of the possibilities is this first one here. So one of the possibilities is on your first throw you get a head, then a head on the second, and a head on the third. So the variable we're interested in here, and this is the number of heads, and so that's the x, and in this case it's 3, so we're getting 3 heads. All right, so what is the probability of 3 heads? Well, if you look at the probability in terms of, on the first, the probability of getting, so you're getting a head, and so and is times another head, and the probability a head is half, and another one, probability is a half. So it's a probability of 1/8 of getting head. And over here, writing it in this form, probability that x is 3. In other words, the probability you get 3 heads is 1/8. All right, so in this next lot, as you can see, I've grouped it into ones where you get 2 heads. So it could be head, tail, tail, head, head. And then in all of those 3, there's 2 heads. Now again, the probability is, because the probability of a head and a tail is a half, it's always going to be a half times a half, times a half times a half, 1/8 for all of that. But now, because we're grouping it into 2 heads, so we're not actually necessarily interested in the individual outcome. What we're interested in is the overall outcome. So we're not interested in whether they got 2 heads first or 2 heads last, or, we're not interested in that. We're just interested in 2 heads. All right, and there's 3 of them, and 3 lots of 1/8, of course, is 3/8. All right, and so the same kind of explanation, rationalization, explanation, whatever you want to call it, holds for these last two. So when there's one head or when there's no heads. Of course, it's three tails. All right, so that's one way we can do that. Now, in terms of probability distributions, we're not going to represent it like this. We're going to represent it in this way here. And this often represented in a table. So x here. X is how many heads, of course. So you can get none, 1, 2, or 3. And then there's the probabilities. The big X, the outcome, is equal to little x. So in this case, probability that you don't get any heads is 1/8, we saw above. 1 is 3/8, 2 is 3/8, and 3 is 1/8. Now, of course, when you notice that, you see that all of that all adds up to 1, which we can use to our advantage sometimes. And in this next example that I'm about to do, I can show how we can use this to our advantage. All right, so this table here then can be used to find probability. So here's a couple of examples. So probability that at least 2 heads, at least means that many or more. So that's x is greater than or equal to 2. And so, of course, that is probability that x equals 2 plus the probability that x equals 3. And so when we look at that, you got 3/8 plus 1/8, which is 4/8, which is equal to 1/2. All right, so now this one here, probability that x is not equal to 1. So when I mentioned up here earlier, I mentioned that we can use the fact that all of this adds up to 1, all the probabilities add up to 1, that we can use that to our advantage sometimes. So the probability not equal to 1 is probability of 0 plus the probability of 2 plus the probability of 3. So in this case, it's not too hard to just add those up, but if there was lots more, then this following technique that we can use, we can say, okay, so we don't want it equal to 1, so what that means is that that's the same as everything minus the probability where x is equal to 1. So that, of course, then is 1 minus 3/8, which, of course, then is 5/8. All right, so there's another strategy. All right, so we can get these tables and use these tables to find out certain things, which is nice and handy. But if we need to develop these tables, how do we actually do that? Well, it turns out it depends. And it depends on the size of your population. So a small population, so consider a bag containing 6 balls. Sorry, 6 blue balls, 4 red balls. A random sample is drawn. Find the probability there is 1 blue ball in the sample. So with small samples, so we're talking about blue balls here. So if I draw it initially, there's 6 blue out of the 10. And if I take one out and it's blue, then 6/10 is okay. So if I've taken one, then I now have not only got 9 balls left. Now, if that one I took and it is blue, then the probable now that if or that one that I took, there's only 5 blues left, and so the probability changes significantly each time. So 5 divided by 9, if I have a look at that, 5 divided by 9, see that's 0.55. But 6 divided by 10 is 0.6. So as you can see from that, that's quite a significant difference in the probabilities. So we need to figure out how a way of working it out. And so here's what we do. So for a sample, so let's not worry about whether they're red or blue at the moment. So this is the sample. So the sample, we are selecting 4 balls from 10. Now, remember back to our combinations, selections, arrangements and selections, permutations and combinations. So we can use that to figure out how many that there is. All right, so what have we got for the sample? Then there would be 10 C4 ways of selecting the sample. All right, so that's what it's out of, and so recall that NCR is the same as N above R, which is N factorial R factorial N minus R factorial. All right, but our calculator can work that out for us as well, and that's the method we're going to use in this, but that's just worth recalling. Now, that was our sample, all right? So now what we want to find is the probability there is one blue ball in the sample. So what we're after is this proportion, and I'll put the hat because it's a sample proportion, is one blue ball. So the probability of the sample proportion, one blue ball's not a proportion. The proportion is one blue ball out of the sample, which is 4, so 0.25. So we're looking at the probability that the sample proportion is 0.25. All right, so here's the number of ways we can select our sample, 10C4. What we want to know is, so for that outcome, one blue ball, as it says here, I've been scrolling it out, the outcome we want is 1 blue and 3 red. So there again, and remember then when we're doing probabilities, and means times. And again, if we're selecting, now selecting 1 blue ball, selecting 3 red balls. Now we've got to think about what we're selecting them from. All right, the blue balls are from that blue balls. Now, how many blue balls was there? 6. So that's 6C1. So of that 6, what we're interested in is where we get 1. And of course there's 4 red, and we're interested in then, if we've got 1 blue, then the other 3 have got to be red. All right, so if we're going to put that together, then what we do is get this. So thus, the probability that the sample proportion is 0.25 would be equal to 6C1 times 4C3. That's how many ways we can get that particular outcome over 10C4. And then when we do that, let's go on our calculator. I'll just remind you then from the calculator. So remember, we're in the keyboard, and let me get which one it is. No, it's not. It's there in the advanced. Right. So you got a keyboard. You got to go down advanced, NCR. So NCR. But hang on, let me me get that out of the way. Let's squeeze that there a little bit. Right, so let me go clear that. So what do I need? I need this fraction, so I need to go back and get my fraction template. Advanced, so NCR, so what do we got? We've got 6.1 times the next one, 4C3, 4.3, whoops, 4.3, and then over 10C4, and 10.4. Good buddy. All right, then XE, and there it is. That's in a decimal form. And there you go. We've then got 4 on 35, apparently. All right. So there is, let me just go back here. That's 4 on 35. All right, just make sure I entered those correctly. Yep, 1 out of the 6 blues, 3 out of the 4 reds, and we want 4 out of the 10. Yep, okay, so that's all right. That's what I've got. All right, so as it says, often it's written like that. And so this is given a name, and it's called hypergeometric. So this kind of distribution that I looked at this thing here, that's what's considered hypergeometric. All right, and so the definition of it is the definition of our hypergeometric. So population of size n with d defective objects, the probability of obtaining x defectives in a sample size of n is given by this stuff. So, you know, defective just means what defective is just what we're interested in. Up there, we were interested in blue balls. So population size 4, we want 1 blue ball. That's right, we wanted, yes, we wanted 1. Population of 4, we wanted 1 blue ball. And so the probability of obtaining 1 blue ball in that sample size of 4. And our population was size 10, and there was 6 blue in there. All right, so there is this handout. All right, so should I have given that? That's also in the on the website there, a link to this. All right, so it's a walkthrough on your calculator how we can do things with that. So let's have a look at an example. So this example here is known that 80% of a group of 40 people has been immunised. So this one's written in 80%. So let's have first of all the sample sizes, not the sample size, the population size is 40, and 80% of those have been immunised. So the thing we're looking at is immunisation, and so 80%. Now, with this hypergeometric, we need to know how many, all right, so which is the D, and 80%, its decimal is 0.8, so 0.8, 80% of the 40, means of that 40, 32 have been immunised. Find the probability in a sample of 5 people, so that's n equals 5, that 3, so that's x equals 3, have been immunised. So if we're to write it out, the probability of x equals 3 is equal to, all right, so on the bottom, we've got 40 people and our sample size is 5. On the top, we've got 32 immunised, and we're interested in 3. And so if we've got the rest, if we've got 3 immunised, then we've got to have 2 that are not immunised, and there's got to be 8 of them. All right, so let's go to our calculator and have a look at how we might use that. So in our main screen, if we go to interactive, and then we go to discrete, remember this is distribution inverse to discrete, and so we're Hypergeo, see down here, Hypergeo PDF, and there it goes. So what do we got there? So X is 3, by the looks of it, 3, N was 5, our samples. Oh, and see, it tells you the number of trials from the population, so the number of the sample size, 5 of them. Number of successes, so the number that are immunised in the population, so there's 32 of them. And how many in our group are we interested in? That was 3, wasn't it? No, N, sorry, N, population size. Should have read it, shouldn't I? 40 in this population size. 40. And I'm going to do this one as OK. And so in this case, even though I've got it set standard, it's not programmed to give you an exact value. It's programmed to give it to you as a decimal. And so what we then, what is it, 0.211. So that equals 0.211. So the probability that if you pick out a group of 5 out of that 40, the probability that 3 of those 5 is immunised is 0.21%. 0.211, not percentage, so the percentage should be about 21%. All right, so that's small populations, so we use the hypergeometric, and we're using our calculator, so you just need to use it. You wouldn't be asked to do this with the non-calculator because you're doing NCR for it. Too much mucking around and too much arithmetic to do all those factorials and things, so we will only be using the calculator for this. All right, now if we go to a large population, so a large population, for example, so say I've got 100,000, and of that 100,000, let's say 100 of them has got a particular thing. So if I take that out, then it's 100 over 100,000. But if I now take one out and see what's left, that's 99 now out of 99,999. Now, if I have a look at those on my calculator, so 100 divided by 100,000, got enough? No, I need one more. It's 100. That's what it is. All right, so 1 by 10 to the negative 3. And if now it's 99 out of 99,999, it's 9.9 by 10 to the minus 4. So when I look at these ones over here, so this was 0.123, and this is 0.00099. All right, so you can see the difference between these numbers is not that great. Now we've got a larger population, whereas up here, all the way up here, there we are. So all the way up here, when we did these ones, there was quite a significant difference. Now I've only used 100,000, so if we go into massive populations, like populations of countries, for example, then that difference is going to be even smaller. So for large populations, we can assume that the probability of the attribute remains the same. So we assume probability remains the same after we make a selection. All right, so in this case we use what is known as a binomial distribution. So these are the points here, things about a binomial distribution. So big population. All right, so first of all, each trial is identical. All right, so there's no change there. Two outcomes, success or failure. So again, up in the previous one, we were looking at blue balls. So that's all we're interested in. Anything else, not interested in. So there's two. It could be 5 different coloured balls in that group. We're interested in if they're blue. So they're either blue or they're not. Doesn't matter whether it's yellow, red, green, or orange or whatever. It's either blue or it's not. So same here. Success is blue. Failure is anything else. Probability of success for P is P for all trials, so it doesn't change, and I just talked about how I showed you there an example. So the outcome of a trial does not affect the next, so they're independent, and these are called Bernoulli Trials. All right, Bernoulli was a person, mathematician, did other stuff as well. Bernoulli effect. So if you read Bernoulli Trials, it means all of this stuff. So Bernoulli Trials, it just means, for us, in effect, all it means is binomial distribution, and we use the binomial distribution stuff. All right, so the probability of achieving X successes in a sequence of n trials for binomial random variable is X is given by this. So n above x, so the n above x says how many times this might occur. P to the x, so the probability of success, how many successes. And then 1 minus p, well, this is the other stuff, everything else. And n minus x, so n's the number of trials, how many successes in that have we got. All right, and so x is whole numbers. So 0, 1, 2 or so. And this probability P, this P is the same in every trial. So the probability of success in every trial. All right, so we're going to get to a question. And so this handout that I've given, nicely made by Charlie Watson, will lead you through, lead you through what to do. And of course I will work through that as I go through the example. All right, so here we are, back to the notes. So suppose 10% of batteries produced are faulty. So again, we've got 10% that are faulty. And so that's our probability, or our P, our proportion, is 10%. Now, of course, we don't do it in 10% in percentage, we do it in a number. So as a number, 10% is 0.1. So find the probability that a random sample of 2 batteries, so n equals 3 batteries, n equals 3, random sample of 3 batteries, that's our n, 2 are faulty, so that's what we're looking for, so x equals 2. All right, so if we were to write that out using what I've got above, so the probability that x equals 2, would be n above x. Can I squeeze it in? Not quite. N above x, so 3 above 2, 3c2. Probability of success, 0.1, and we want 2 successes. Then 1 minus p, and 1 minus p, of course, 1 minus 0.1 is 0.9, and that's the other one. All right, so on our calculator, so similar to before, in that we went interactive, we go to our distributions, we go to our discrete, and so this time it's the top one, binomial PDF, x, the specified trials. So how many is it that we are interested in there? We are interested in x being 2, so 2. The number of trials, the number of times we're doing it, selecting is 3. We're selecting 3 times. And the probability of success is 0.1. Okay, and there we go, 0.027. So we can put that down there as equal, 0.027 to 3 decimal places. All right, again, we're going to use our calculator for that, not doing it by hand. As you can imagine, the arithmetic just gets quite time consuming, and that's not really the point. The point's not really about whether you can do the arithmetic or not. The point's about whether you can actually apply this to the situation we are interested in. All right, so that's it about these two. So you've got some questions there that you need to do for some practice now. Of course, if you've got anything you need clarifying, make sure you get it clarified. And as always, have fun.